Okay, hello everyone. One thing I wanted to mention first off is that we've changed the settings for YouTube Live streaming, and it should have a better responsiveness. Like, you should only be about 4 seconds behind me now. And so if there are questions that come up that is really going to take, like me drawing on the slides to do, that's going to be more doable than the 30 seconds we had on the first couple lectures. Also, I think I mentioned it last time, I had my broadcasting software set up to a resolution which was almost 720, but not quite. And I didn't realize YouTube was going to downgrade it to 640. So I've upgraded mine to 720. I don't want to run into lag issues because of too much, but we're going to try a 720 resolution with a lower latency. Should make things a little better for all of us. On the labs, I put the announcement on Piazza. Make sure you go to on Canvas. On the left-hand side, there's lab schedule. So make sure you go view the lab schedule there, and that's when we're going to be holding online labs, and we've got the staff are filling in links for things. So we've already got Tuesdays is already linked in there, and then we're going to add in links for other days. And so we've got there's still a few Wednesday and Thursday that need linking, but we'll get those done before Wednesday and Thursday come around. And then after that lab gets recorded, then down at the bottom, there'll be a link for the YouTube recording of it. Okay, next thing that's come up over the weekend, I didn't notice until today because I've been spending so much time on 281 stuff. I spent all day Saturday and most of the day Monday working on 281 stuff. So with the GEO, the Graduate Employees Organization, voting to strike, that affects 2 of our staff members. So we have 2 GSIs. So if they do go on, if they do follow the strike that GEO has voted for, it shouldn't significantly impact us. We'll make sure that if we have to swap around who's covering a lab or something, we still get those covered in the coming weeks. And so we'll see what happens with that. On the Project 1, so I posted on Piazza last night, so Project 1 is now available on Canvas. There's a tutorial video which I created yesterday, and it's linked in the project spec, it's linked in the Piazza post, and as I was getting ready to present like 10 minutes ago, I realized I should link it in the slides here also. Read through the spec. The video and like the hints and advice section of the spec are not going to be as useful until you understand like really what the project does. The video was intended more of like tips for getting started and order to do things in and things like that, and not actually what the project is about. I think the project explanation is pretty clear on that. The important thing is, like I said in the video, is don't be intimidated by the length of the spec up front. You don't have to understand all of it in order to start working. So you can do things like deal with the command line options. There's a section of the spec that lists the command line options. So you could start doing that first. And then you could start reading the dictionary. You know how to read input. For almost all of our projects in 281, there is one version of Project 3 that this is not true for. But all of our other projects, other than one of our versions of Project 3, read from CN. You're going to read all of your input from CN. The redirection is going to be done for you on the autograder. Now, granted, if you've got Xcode or some other IDEs, you have to do some stuff with the Xcode redirect to get redirection to work, but that's just because of the IDE. When you're on the autograder, it's going to take care of redirecting the input for you. So you should always be reading from CN. So for Project 1, you shouldn't be opening files, you shouldn't be creating a file stream or anything like that. Just read all of your input from CN. The sort of like mini checkpoint here is like soon you should understand the command line options, get those coded because they're going to be similar to what you did for Project 0. Definitely watch the video. I gave some really helpful tips about organizing your code and how to do the get options and making a class and member variables and stuff like that. So start getting the command line option parsing and the test files of your own. Start thinking about doing those soon. When you run this program, this whole project, it involves searching using a stack or searching using a queue. And the stacks, and we're going to learn more about this later on, the stacks do what's called a breadth first search. The stacks do a depth first search. The queue does what's called a breadth first search. And we're going to learn more about that later on. Simple takeaway is depending on what you treat the search container as, it will affect the morphings and which word changes to which other word. And there's some other good things in Canvas. There's a file called Project 1 Examples for Letterman. And that'll show you a bunch of useful things about how the different search containers could affect the output and how they could make the output different. Okay, so we're going to start with the meat of today's lecture, which is about runtime. So the things that affect the runtime of your program are the algorithm that you choose, the implementation of that algorithm, which is partly based on the skill of the programmer, the computer that it's running on, the CPU speed, the memory speed, etc., things like compilers, which compiler might make a slight difference, optimization flags and options given to the compiler make a bigger difference, and other things that affect it is other programs running in parallel. And that one you don't have much control over. When you're running on your own computer, you can limit the other things you're doing at the same time. On the AutoGrader, we have a machine with 8 CPUs, and only 6 students are allowed to be running at a time. So the other CPUs are doing things like dealing with backups, dealing with defense of the server, the web server itself, just students connecting to the web server, things like that. When we do final grading of your projects, that will run 1 student at a time instead of 6, and that will really try to minimize those other effects of other things going on at the same time. And if you go to the AutoGrader and it says something like this AutoGrader is not accepting submissions now, you should use the other AutoGrader, that shouldn't occur very often. Sometimes it'll happen when we're making a change, like changing something on the AutoGrader to make it better. But the big one will be a couple days after Project 1 is due, I will turn off submissions to AutoGrader Run 1 while I run the final grading, and then when that final grading finishes, it'll automatically start accepting submissions again. And we do that because if you submitted to AutoGrader 1, like Project 2, let's say you submitted Project 2 or Lab 3 or whatever's coming up at that time. Say you submitted a Project 2 or a lab at the same time as final grading was running. If you submit it to AutoGrader 1, it gets in the queue behind the, whatever's left of the 900 and some students, and then you aren't allowed to submit the same project on AutoGrader 2 until it finishes on the first one. And so we don't want you sort of locked out of submitting something at all for a day and a half. So if you see that it's not accepting submissions, just try the other AutoGrader. And the 2 AutoGraders have identical hardware. When you're inside, that's a good point. When you're inside of an IDE, they do debugging by default. With Visual Studio, it's very easy to change that. It's like a menu up at the top. You can change from release to debug really easily. Inside of Xcode, I know there's a way to do it, but I can't remember it off the top of my head. But when you do it, when you go into the command line and you just type make, we get a -03. If you do make all, you get both. So you'll get, if you do make all, like with project 0, you'll see you get a project 0 and you get a project 0 underscore debug. And so this is the one that's, this one is the -03 and this one is the -G3. Oops, G3. So make all creates both of them. Make just makes the project 0, make all creates both of those. And then you can decide which run to run at the command line. If you're running your code inside of Visual Studio or inside of Xcode and you run the biggest input file we give you, it might take a while because it's a debug build. So it could take longer if you're inside of your IDE. And the last big thing that affects our runtime is the amount of data, that input size. So if we keep the other factors constant, same CPU speed, same compiler, same memory, same machine, minimize other things that are happening at the same time, if we get rid of all of those or keep them as constant as possible, then it really comes down to the input size is the most important thing, if everything else stays the same. So if we say, hey, I doubled the size of the input, does the program take twice as long to run? Well, it depends. It depends on the complexity of the program or the algorithm we're running. So right here we've got two graphs. I would say this one looks like linear, O of n. This one looks like O of n squared, just as an eyeball estimate. So it might be that doubling the input size makes it take 4 times as long. Or we could have something more complex. When we go to project 4, there's going to be part of project 4 that's O of n factorial. So if I look at n equals 5, we multiply it out, we get 120 is the amount of operations it takes. If n is equal to 10, we get 3.6 million operations. So it would take way longer for one part of project 4 when we're on the factorial growth. So we could see a linear increase in size. We could see a doubling in size when we double the input. We could see a factor of 4, or it could be even more. It all depends on the implementation of the algorithm. Now, what do we mean by input size? Do we want to talk about the number of bits inside of the data? Like, is it a 32-bit integer or a 64-bit integer or a 64-bit double? We probably don't want to go down to that level of bits. What about if we say, hey, it's the number of items, whatever an item is? Well, what is an item? Is it one integer? Is an array of integers one item? Is it a digit within that number? Are we talking about a string, like a bunch of characters? Is the input size the total number of characters, like each string multiplied by the average length of those strings? So n could be different things here, depending on what we're working on. For project 1, I would say the n I would usually refer to as the size of the dictionary. And yes, I have to look at each character, but most words don't have more than about 10 or so letters. It gets really rare to have words that have more than 20 characters. There aren't a lot of those. So in effect, most words in English and in a dictionary have a maximum limit to the length, which is, on the order of like 2 digits. And so effectively, they all have a length that is on the order of like 10. So really on project 1, I would say our n is the number of words in the dictionary and less effective the length of the words themselves. So we're going to talk about n as our input size. F of n is the maximum number of steps taken by an algorithm operating on an input of length n. And then we'll talk about a complexity class, the big O of f of n, and we're going to talk about that more later as we get along through today and the next lecture. So input size, sometimes n is easy. If I'm doing a graph, which we're going to do later on in the semester, in the last couple of weeks, then n might be, I could just say, hey, n is just the number of vertices plus the number of edges. But when we do the graph theory, we're actually going to look at more different types of complexities like e log v, or e times v, or v squared log e. So it might be convenient to have only one variable representing the size, but sometimes for more complex situations, we're going to have two variables to represent the size. Now we've got a bunch of common complexity classes here, from fastest to slowest, at least of the ones that are listed. So we've got O of 1, constant time, logarithmic time, linear. N log n, I've heard it referred to as log linear and linearithmic. I don't really like either of them. I just generally say n log n. Quadratic, which quadratic is a subset of the polynomials, but it occurs so often that we will tend to say quadratic when it is a n squared rather than saying it's a polynomial. Then all of the polynomials are within the class. Then there's, beyond that, we get exponential time, factorial time, doubly exponential. There are things that are doubly exponential. Things like if I say, if n is the number of bits, how many operations are there that can take place on two n-bit numbers? So like if we enumerate all those possible operations, there's addition, subtraction, multiplication, etc. There's actually 2 to the 2 to the n possible operations. And yes, this is in growth order. So 2 to the 2 to the n does grow faster than n factorial. And there are things that grow faster than these. We're going to see one later on in a few weeks, I think. Yeah, in a few weeks, I think. We'll see a class that grows even faster than these. But they get rarer. Beyond factorial, it gets kind of rare for these to occur. We've got an example here of just what the runtimes look like and how fast things like exponential go off the top of the chart. So when we start talking about, hey, I've got my steps here in my algorithm, what makes up a step? Well, we could list a bunch of primitive operations, and those primitive operations can be categorized things like variable assignment, arithmetic operations, things like plus or minus, comparison, is this thing equal, is it less than or equal to, is array indexing or a pointer reference, so either looking at like a sub square brackets I, or I'll often say a sub I. So meaning a subscript I. So I'll often say that out loud, and I forget sometimes to explain that. So I'll say a sub I, which, wow, my handwriting is really terrible today. Okay, so a sub I, or a pointer reference like pointer, arrow, element, or dereference pointer. A function call, not counting the data, so not counting the parameters. A function return, not counting whatever gets returned. We could call these all basic steps. And then most programs could be analyzed based on these basic steps. So we've got an example here. We've got a function, and notice I didn't count the function call here. I didn't count line 1 calling the function, because one thing we want to be careful of is we don't want to double count it. We don't want to count, hey, someone had to call the function and then the function call had to be received. So I didn't want to count it twice, but we could put another one step in for line 1. So line 2, we've got sum equals 0, variable assignment. In line 3, it says 1 plus 1 plus n times 2. We'll get back to that one. We're going to come back to line 3 in a minute. Line 4, it says 1 step. Really, we could also relabel this as 2 steps because it's really an arithmetic and an assignment. So we could really count that as 2 steps. And then line 6 is 1 step, the return. And hey, if we modify this a little bit, if we add 1 step in here, then we would have to go, instead of 4 plus 3n, we'd have to say 5 because of this one, plus 4n because of that one. But we would still say this one is O of n. So even if we disagree a little bit about the constants, we're still going to get the same complexity class for this. So now let's look at the line 3. Where did that come from? So we got another slide for that, and then we'll come back. So our basic for loop has 3 parts: initialization, test, and update. The initialization happens once. That's one of the things added in. The test is performed every time the body of the loop runs, plus 1 more time for when the loop ends. So if I say, hey, run a loop for I equals 0, I less than 3, that I less than 3 test happens when I is equal to 0, 1, 2, and 3. So if n was equal to 3, this test happens n plus 1 times. It's got to fail once and succeed n times. So that's our test, gets performed n plus 1 times. The update happens after the body of the loop runs, which is n times. So that's where we get our 1 plus 1 plus 2n. So that's where that 1 plus 1 plus 2n came from in line 3. So that's our 1 plus 1 plus 2n. And then the second function down there, function 2, we could do the same thing. We could then multiply out those polynomials, add everything up, and we get the 3n squared plus 7n plus 6, or we would later on, we're going to simplify that to O of n squared. Now we still haven't gotten to how we simplify that yet, but we'll get there eventually. But I expect you to remember a little bit of this stuff from 280. So the reason we got the 3n in there was the 3n or the 4n comes from the 1 step or 2 steps, because, hey, the body of the loop, this line of code here is going to run n times. So that's why we got the 3n or the 4n, is that's line 4 happening n times. And that's why I indented line 4 to show that, hey, if that loop's going to happen n times, line 4 is going to happen n times. Okay, so we did that slide. So here's an algorithm I want you to take a look at and think about this one. What we want to do is we want to do some multiplying. And we talked about this one, I think it was last time on Thursday. So this was the one where we multiply the input to get the output. So if we had, for instance, if my input was 3, 1, 2, my output would be 2, 6, 3. So it's the multiplication. So element 0 of this array is the product of everything except element 0 of that input array. So here's one of the ways that we wrote this, was using the double nested loop, which gives us the O of n squared. We've got our, I thought I had another slide there. So we've got our loop that's going to run n times. We've got our loop that runs n times. We've got an assignment in here that's going to happen approximately O of n squared times. Now we could get the longer formula, the so many things times n squared plus so many things times n plus some constant, but we really want to get to the point where we worry about the big O, because on the exams, we're not going to ask you for that level of the 3n squared plus 7n plus 6, because it's so easy to be off by just 1 on a constant somewhere and still get the n squared. So on the exams, we're not going to worry about that level of n squared plus 7n plus 6. we want to get to the big O complexity class. Okay, and then the other one, we had the faster version of this that has some problems. Remember, if there are zeros in the input, our product is 0, and then we might divide by 0 when in the second loop. So this one is going to be, we're going to have an O of n loop, followed by an O of n loop. So O of n plus O of n is O of n. And we're going to learn about why we can drop the constants in just a little bit here, coming up in a few slides. So that was our 2 algorithms for that multiplication of everything except the current element. This one has bugs if there's zeros in it. And I suggested, hey, one of the things you could do is rewrite this, use a couple more variables, a little bit more work, and get this to where it works if there's 1 0 in the input. If there's more than 1 0 in the input, you should get all zeros in the output. If there's 1 0, you should get one element in the output that's not 0, but you got to be careful with the product. Now, here's the definition of big O. So we would say f of n, the function f of n, is equal to big O of g of n if and only if, and sometimes you'll see us abbreviate this as IFF, if and only if. So if you see that, IFF means if and only if. So if and only if there are constants c, which is greater than 0, and 0, which is greater than or equal to 0, such that f of n is less than or equal to c times g of n whenever n is greater than or equal to n0. Now, what that's showing is, let's look at the graph down below. What it's showing is that we've got a point where these two graphs cross. So we're trying to answer the question, is n, that's f of n, so that's f of n, is f of n big O of g of n? So f of n is n, g of n is n squared. So really what we're trying to say here is n bounded above by n squared? We're trying to get, is it an upper limit on it? So if we found the point where they cross, that could be our n0. Now, we don't have to find the exact point where they cross. We just have to find any point beyond which a constant times g of n is always greater, or greater than or equal to. So if we can find any point, like I could say, hey, I'd like an n0 is equal to 1.273. That's equally valid. I just have to demonstrate that they exist. I don't have to find the perfect values. I've just got to find a pair of values. Now, what's my c here? I showed that my n0 would be equal to 0, or n0 is equal to 1.273. Doesn't matter which one I pick. What do I pick for c? I could just pick a constant c is equal to 1. So I've found a set of constants, c, which is not 0, n0, which is greater than or equal to 0, such that c times g of n is greater than or equal to f of n everywhere beyond n0. So that's one way of showing that something is, f of n is big O of g of n. Now the other way, now this one is a sufficient but not a necessary condition. What this means is that if this formula works, then you've shown that f of n is big O of g of n. But if this formula doesn't work, you haven't shown anything. You've just shown that this condition didn't work, but you didn't disprove the claim. So we want to know, is f of n big O of g of n? So we've got an example here of using this approach. So the approach says we take the limit of f of n divided by g of n. We take that limit as n goes to infinity. If it's equal to d, d means some constant. So if there is some constant that this limit is equal to, then f of n is big O of g of n. That constant has to be a constant. It has to be less than infinity. So if this limit is a constant, then f of n is big O of g of n. So we've got two examples here. We say, is log bounded above by 2n? So we've got to show that the limit as n goes to infinity of log n over 2n goes to a constant. Well, at the beginning, we've got infinity over infinity. Now, you can use your calculus. You don't have to have had calculus to take this class. This method always works. This method sometimes works. I'd rather learn the method that always works. But we can do this sometimes, and sometimes this is easier. If you can do it, great. If you can't, you can always use this method. So we've got a limit that goes to infinity, but we can apply L'Hopital's rule. We get the constant d is equal to 0. That constant is less than infinity. Therefore, it's true. Log of n is bounded above by 2n. Next example says, I want to know, is the sign of n over 100 bounded above by 100? Now, we try to apply this method. We've got f of n, we've got g of n, we take the limit, and the limit does not exist. The limit does not exist, therefore we haven't proved anything. But our graphical method works just fine. If I graph this out, I'm running out of room on this page to graph in. Let's see if I can go back a page. Okay, we'll use this bottom portion here. So if I graph this out, the sine of n divided by 100 looks like this. That's a terrible sine curve, but pretend I can draw one cleanly. And 100 looks like that. So yeah, I can pick n0 equals 0, c equals 1, and it works. The limit does exist, and sine of n over 100 is bounded above by 100. This method didn't show anything. It didn't prove or disprove it. It just showed that the method failed. And if the method failed, we didn't learn anything. But we can always go back to the graphical method, find some constants, and we're good. We just have to have an upper limit. We don't have to have the perfect upper limit. We just have to show that the upper limit exists. And it could be, so my c could be, say, smaller than 1 maybe. We are not going to ask you to prove these on an exam. What we might do is we might give you code like this and say, what's the big O? Or better yet, we might say, what's the big theta? And we're going to talk about what big theta means in a minute. So we might give you code. We might say, what's the tightest possible bound on big O? So here we would say it's O of n. So we won't ask you to do the proof. We'll ask you to give us the final answer, like it's big O of n, or it's big O of n squared. Okay, so we wanted to look at back on the dropping the constants part. So we've got an example here, one that can be shown with either method. So I want to know, is 3n squared plus 7n plus 42, is this big O of n squared? So by my definition, I just have to find some constants. So I graph it out. I graph out c is equal to 5. And so here I just said, hey, let's just set g of n equal to 5n squared. So yeah, really g of n is n squared, but I wanted to graph. So this graph here, this is 5n squared, and this is f of n, the original f of n. Now, there's an n0 there, and if we were to zoom in, we'd see it's like 3.7 something. I don't care what the exact value is where they cross. I'm going to say 4. 4 is a good enough n0 for me. So if n0 is equal to 4, beyond that, the 5n squared curve is always bigger, so I've found my constants. n0 is equal to 4, c is equal to 5. I've found my constants. I've got my proof. It's done. Does c equal 4 work also? Yeah, c equals 4 would work just fine. c equals 3 would work, but we might have to find a bigger n0. So if we change our c, we might have to change our n0 also. We just have to find a pair that works. So if I choose like a c of 10, maybe my n0 will be smaller. I just have to find any pair that works. Now this particular example is one that we can run through the sufficient condition. We got the limit of 3n squared, 7n plus 42 over n squared. We apply L'Hopital's rule a couple times. We get the limit is equal to 3. So we do have a d that's less than infinity. This method works also for that one. So how did I get c equals 5? I picked it out of my brain. I just said, hey, I think 5 looks like a value that's going to make it bigger. Really what I did was I looked at this 3 out here. I looked at that 3 and said, hey, I'd like a constant bigger than 3. That'll make it easier to find an n0. So it wasn't just totally random. I picked a constant bigger than the coefficient of the largest term. So I looked at it, I said, hey, the largest term is 3n squared. Let's pick a constant a little bit bigger than 3. That'll make it easy to find an n0. So that's why we've got the ability to drop these constants. Not only can we drop the constants like the 3n squared, we can also drop the lower order terms. So when we look at the big O notation, really what's the most important thing for finding the big O is the largest order term. And once we find the largest order term, we can remove the constant from out front of it. So our general rule of thumb from our method of determining this is that the lower order terms can be ignored and the coefficient of the highest order term can be ignored. And that's really how, if we really need to determine a, c, and an n0 that work, that's where I would start, is eliminate all the lower order terms and then look at a constant bigger than the one that's already there. And that'll give me a valid c. You could even pick c equals 3. It doesn't have to be bigger if it's, this one we're going to have to go bigger than 3. I don't think 3 would quite work because then the 3n squared plus 7n plus 42 is going to be bigger than 3n squared everywhere. There's no n0 if c is equal to 3. So we've got to find something bigger than 3, like 4 or 5. Okay, we've got a bunch of properties here that might prove useful to you during the semester, some more useful than others. I'm going to demonstrate one right now, and we're going to look at using a few of them in another slide. So one of them, this one right here, that one right there can sometimes be really useful to you depending on your calculator. So what this says is that if you want the log base a of something and you don't have a base a button on your calculator. So let's say, for instance, I want the log base 2 of 1,000. I look on my calculator and I don't have a log base 2 button. Well, that's okay. I can just take the natural log of 1,000, divide by the natural log of 2. It's also equal to the log base 10 of 1,000 divided by the log base 10 of 2. So as long as you've got a log button on your calculator, you can calculate any log base. So if we did this, we'd find the log base 2 of 1,000. It's approximately equal to 9 point something. I'm going to say, guesstimate in my head, 9.9-ish. It's a little less than 10. But we can pull out our calculator and do exactly. My calculator's 6 feet away charging. So anyway, so that's one of the relationships there. Another really useful one is up here. This one says if you've got the log of something to a constant power, you can take that constant out front. So if you've got like log of n squared, that's equal to 2 log n. Okay, so using those, and I brought a few of the more useful ones. Not all of these are useful, but I cut down the list a bit. And we've got some questions here. I want you to answer true or false for each of these. So true or false for each of those, and then after you're done with that, it says find an f of n and a g of n. Tell me two functions such that neither one is an upper limit of the other. So that neither one upper bounds the other. So what you can do is you can talk in the chat about this one, how you would use it, which, if any of those relationships is useful. Some of these you can just solve using what we learned a few slides ago. So I'm going to mute my mic here, let you talk about this for a few minutes in chat, and then I'll come back. Okay, had to remember to turn my microphone back on. Okay, so let's look through these. All right, so true or false for the first one is a really big constant bounded above by 1. Sure, I just need a bigger constant. I can choose c is equal to 10 to the 101st power. And then any n0 will work for that. n0 is equal to 1. Okay, next one is something with n to the 4th plus some n cubed bounded above by n squared. So that first one is true, this one's true, yep. Okay, is 3 to the nth power bounded above by 2 to the nth power. That one's going to be harder because as I could pick a big constant and I could find an n0 and a constant that made it bigger, but if I get a bigger n, that 3 to the n is going to become bigger again, and then I need a bigger constant. So anytime someone makes the n bigger, I need a bigger constant. So this one's going to be false. That's not going to work because the bigger n is, the bigger the constant I need. That means it's not a constant anymore. Now, is 2 to the n bounded above by 3 to the n? Yeah, I just need a constant like c equals 1 and n0 is equal to, say, 2. It's going to be bigger all the way out. So, okay, what about 45 log n plus 45n? Is that bounded above by O of log n? This one was to get you to see that we might not write it with the largest term first. This is the largest order term. That's the one we can cross out. So that one's, that one is true. This one's going to be false because we got the wrong term. We crossed out the first term instead of the largest order term. So then in the next one is log of n squared bounded above by O of log n. That one goes back to, let's see, which one of those equations is it? This one. So this one we can use to show that this one is true. So we can take that 2 out front. And then the next one, log of n, the log squared, is O of log n. Now that one's a little bit harder. One thing that we can do here to make this last one a little bit easier is substitution. Let's say I said, hey, let's let x be equal to log n. So then my question becomes, is x squared equal to big O of x? And that one's false. So that one I found the easiest way to do that one was to use a variable substitution. Okay, so the next one here, we got an f of n and a g of n such that neither one is an upper bound for the other. So you're true. So I've seen people in the comments as they went flying by. It's really hard for me to keep track of all the comments sometimes. So I saw a couple answers in there. So we got all those are trues and falses. For the functions, neither of which is an upper bound of the other, one example is sine and cosine. I saw someone else that had something like n and tangent of n, because tangent of n looks something like, terrible tangent drawing ability, but tangent of n looks something like that. So it's a discontinuous function. So that fails. These are things that don't generally come up in computer science. We're generally not going to see a complexity of a function that's sine or cosine or tangent. But they are good things to remember for breaking the examples, like counterexamples. These things are good for counterexamples, but they aren't going to come up that often in real algorithms. I have seen some odd things in algorithms that you might not think would occur. So there are algorithms that have things like a complexity of square root of n or log of the log of n. So those things do happen and they work with the graphs. There is something that bounds them above. So those are odd looking things that can happen, and the bounded above still applies to them. But the ones that we had to break this example of two functions that don't bound each other, that one are things that we wouldn't generally see. But we could see odd things like those two examples in real algorithm complexities. Okay, so big O, big theta, and big omega. So we've talked about big O. So big O is our asymptotic upper bound, and we've got the definition here. So the asymptotic upper bound. So asymptotic, remember, means as n gets large. As n gets large, we have an upper bound. And so we've got our definition, and that definition is just what came from the slides earlier. And then we've got our mathematical definition. There exists an n0 and a c, such that for all n greater than or equal to n0, f of n is less than or equal to c times g of n. Excuse me. The examples at the bottom, so I've got if f1 of n was 2n plus 1, what are some things that are an upper bound? O of n squared, n cubed, 2 to the n would be an upper bound, n factorial is an upper bound. N log n would be another upper bound for f1. For f2, it would have to be n squared or greater. So like n squared, n cubed, 2 to the n factorial, n to the nth, etc. N squared log n would be bigger than n squared. So those are all asymptotic upper bounds. Now, big O doesn't lend itself well to exam questions, because if it was a multiple choice, you just pick the biggest one and you're right. And if it's fill in the blank, you just say, well, you know, I can't imagine anything bigger than O of n to the n, so that's got to be a valid answer. And it works, but it doesn't show that you really learned that much about big O other than how to make things big. So on the lab and exam questions, we'll tend to do one of two things. We'll tend to ask you, like if we give you code, say, we give you code, we ask you what's the complexity. We're either going to ask you what is the big theta, or we'll ask you what is the tightest possible big O. So we want the upper limit that's correct, not the upper limit that just happens to be big. So on the exams and the labs, when we give you code and we want the complexity, we'll say we want the big theta or we want the tightest possible bound on big O. Now sometimes big O really does make sense. Let's take a simple example of why big O is really useful though. Is if I said linear search. What's the complexity of linear search? Linear search is big O of n, but it is not big theta of n. Because in the best case, it's O of 1. In the best case, it's big theta of 1. In the worst case, it's O of n, and in the worst case, it's big theta of n. But linear search in general is not big theta of n because the best case is better than that. So if we asked you, what's the tightest possible big O of the worst case, you'd say O of n. If we said, what's the tightest possible big O of the best case, you'd say O of 1. If we ask you for the big theta, worst case big theta, or best case big theta, those exist. So sometimes big O and saying the tightest possible bound on big O really is meaningful because then we can ignore the best case, worst case, average case, etc., and just figure out the tight upper bound on it. And really, when we're looking for the tight upper bound, we're really looking at the worst case. So if we say the tightest possible big O, we really mean the worst case big O, but the one that's tight up against it. I wouldn't say, if someone asked me what's the complexity of linear search, I wouldn't say big O of n squared. It's true, but it's misleading and lazy. Okay, so we've got our big O notation. We've got our, and let's talk about it. So sort of you threw out these examples of big theta before we went through them. So I'll just leave those up there. So let's look at the other end. Let's look at big omega. So big omega is the asymptotic lower bound. So that's give me something that's less than or equal to reality. So the definition of big omega, almost exactly the same, except we change the sign right here. We change it to a greater than or equal to. The n greater than or equal to n0 is still the same. That didn't change, but the relationship between f of n and c times g of n changed. Mathematical notation, almost the same except for the little change there. And then for some examples. So I say f of n is, f1 of n is 2n plus 1. I could say that big omega of n is valid, big omega of 1 is valid. There's one more common one that fits in here, big omega of what? Log n is the third of the common ones that fits in there. Okay, what about the f2 of n? f2 of n is n squared plus n plus 5. I could say it's big omega of n squared, big omega of n, big omega of 1. I could say it's big omega of log n, or it's big omega of n log n. And I've gotten terrible at writing omegas over the years. I used to be better when I was an undergrad. Did this in double E classes all the time. Okay, so there's our 5 most common big omegas for f2. Now, big theta, it says, is an asymptotically tight bound. So it's going to bound it from above, it's going to bound it from below. The change we had to make here is we've got to find 2 constants, C1 and C2. So we find two constants, C1 and C2, so that C2 times G of n is greater than or equal to, and C1 times G of n is less than or equal to. So they could both be equal to. So for example here, we've got f of 1 of n is big theta of n, or sorry, is 2n plus 1. We would say the big theta is big theta of n. It's the only one that bounds it both above and below. And I could make a, for example, for this one, I could say, hey, C1 is equal to 1, C2 is equal to 3, and we've got a, and if we find an n0, like n0 equals either 0 or 1, and we've got a valid C1, C2, and n0. So then F2 of n is n squared plus n plus 5. Big theta, there is only one big theta. It's big theta of n squared. Okay, now let's do an example of log time. Now this one is sort of a made-up example. It does something. We're not going to worry about what it calculates. It's function 3. It does whatever function 3 does. But if we look at the complexity, so we know the initialization in line 2 is going to take 1 step, line 4 is going to take 1 step, or we could say 2 steps, who cares? So line 4 is going to take 1 or 2 steps, but line 4 is inside of a loop. We got to know how many times that loop runs. Well, I claim that loop is going to run about log n times. It said here approximately. The loop is going to run approximately log n times. And every time the loop runs, it's going to do an update, it's going to do a test. The initialization happens once, the test happens once when the loop ends, and it also happens approximately log n times the test happens. So how did I get to that approximately log n? Well, let's look at the bottom of the slide. So I said, what if I had n items and my n just happened to be equal to 2 to the k? So I said, what if n was exactly equal to 2 to some power? Well, if n was exactly equal to 2 to some power, then if I divide it in half, every time, I will go from n items down to n over 2 items, down to n over 4 items, down to eventually I'll get down to 1 item. How many times did I have to divide by 2? K times. Well, if I chose an n that's exactly equal to the k, then k is exactly equal to log n. If I chose an n that wasn't exactly a power of 2, k would still be on the order of log n. So for example, let's say I chose n equal to 10. So if I started out with n equal to 10, then I'd have to do this with 10 items, 5 items, 2 items, integer division, remember, 2 items, and then 1 item. So I had to divide it 3 times. What's the, oh great, now we need to know what's the log base 2 of 10. Well, that's equal to the log base 10 of 10 divided by the log base 10 of 2. Oh, what is that? Well, we don't know the answer to that, but so that method didn't help. What about, let's learn our powers of 2. So let's look at this. Log base 2 of 10 has got to be greater than the log base 2 of 8, which means it's greater than 3. It's a little bit bigger than 3. It's 3 point something. But it's also log base 2 of 10 is less than the log base 2 of 16. So 4 is greater than the log base 2 of 10 is greater than 3. So log base 2 of 10's got to be between 3 and 4. We had to divide about 3 times. So that's why I said approximately here. Sarah, we're going to get back to that question later on. We're going to get back to divide by 3, etc. So if it was divide by 3, we could say log base 3 of n. But we're going to come back to that log question, log base 2, log base 3. We're going to come back to that later on, I promise. Okay, so there's a couple other examples here of log base time that are less made up than that one. This slide, sorry, we really need to update this slide. We had 4 examples on this slide, and Professor Darden thought the other 2 examples were too contrived, and so he deleted them, and I forgot to rearrange this slide to be formatted a little bit better. So the bottom right one is B search. Sounds like binary search. Now, maybe a little bit different than the way you'd like to write it. You'd probably like to have passed an array and the size of the array and the value to search for. And maybe you'd like it to output an index. Well, this one gives pointers, and it's giving pointers in a sense like this. Inclusive, exclusive. So we've got 2 pointers into the region search, inclusive, inclusive on both ends, and we try to find the pointer where it occurs, or we return null pointer if we never find it. So that does a binary search, but it's done doing pointers. On the left one, log B, basically this calculates the log base 2 of n, the integer. So it takes, and it says that in the comment, it basically does this. It finds the log base 2 rounded up. And it does that by dividing by 2 until it gets a result that's too small. And then it returns the number of times it had to do that. So there's 2 different things that run in log time. Now the question down here, how can this code be optimized? Well, it's already O of log n. We can't make it faster than O of log n. What we can do is we can make the constants better. And we're going to come back to this one. How can this one be optimized? We're going to come back to that one in a future lecture. We're going to see how we can reduce the constants of binary search to make it faster. And we're going to make it, actually, we're not just going to make it faster, we're going to make it more generic, more useful. We'll see that in a future lecture. So when we talk about complexity analysis, we're saying, hey, we've got these basic steps. Each step, we're going to assume each step takes a constant amount of time. It doesn't mean that like assignment and multiplication take exactly the same amount of time, but it says they all take a constant amount of time. Okay, so then if we assume every basic step takes a constant amount of time, if I give you an algorithm, an input size n, how many steps are needed? And what is that trend? What is that big O or big theta? So we want to know what's this trend as n becomes large. What's our asymptotic complexity? How do we measure it? Well, we express the rate of growth, we find how the algorithm grows, and then we find the big O notation that corresponds to our growth. Why do we care? Well, a couple reasons. One is it tells us how well an algorithm scales to larger inputs. So things like bubble sort are n squared. Bubble sort is a perfectly valid sort when n is not insanely large. But when n gets really large, bubble sort is not a good enough sort to get things done quickly. We need a better sort. So we'd like to know sometimes, hey, I've got a small n, as long as the complexity isn't like in the factorial range, if it's just, n squared, n cubed, a small number, 20, 30, who cares? Turns out, I found out when I was doing my PhD research, when you get up to like n equals 900, n cubed makes a difference. And n to the 4th, oh my gosh, is it crazy. So even for things that I would have referred to as small for n squared, they get unreasonable for n to the 4th. The other thing is, let's say we got a hypothetical situation. You go and you work for a company, you get your degree, you get a job, and your boss tells you, hey, the people down in marketing, they're getting this commercial ready, and we want to be able to make this claim about how good our product is and how fast it is, and we want you to prove it before this commercial goes public. Now, a bad answer would be 2 weeks later saying, boss, my program's still running. I think it's making progress, but I'm not sure. That would be a terrible answer, because that would be an answer that either loses you a bonus, loses you a job. A better answer would be, as the moment your boss asks you that, you can come back and say, you know what, I can't answer that question, but really no one can answer that question. It's too complex a question. We don't have time for it to run before you want to get this commercial out. So, and we can say, it's a matter of complexity. This is a well-known problem. This is a well-known problem that has a very large complexity. This N is too big. What can we do? Well, maybe we can find a slightly weaker statement to make that runs faster. I'll give you an example from my PhD research, which was doing DNA analysis for forensic DNA samples. I had this program that ran like two-way mixtures and three-way mixtures, and the three-way and the four-way took a really long time, and I had to really limit the number of things I could analyze. And then one of my advisors asked me a question, and he said, can we do this? I said, no, we can't do it because we don't have the prior probabilities. And he said, well, who has the priors? I said, the criminals, and they're not telling us these prior probabilities. And if you know Bayesian statistics, you know what that means. If not, that's okay. But I had written this program that ran I ran the two-way samples, was simple. Three-way samples started taking a while, and the four-way samples was like, is it even running? And so I had it print out like what it was doing. And it was really, really slow, but it was making progress. So I had to limit my input size. So he gave me this different question, which I couldn't answer. He said, can we weaken the question? Can we answer something similar? I said, I don't know. Let me think about it. And I thought for like a month. And I came up with a solution. And the solution does five-way mixtures in 1 second for things that three-way mixtures used to take 30 seconds. So I found a much better way of doing them. A slightly different question I answered, but a much, much better complexity. So when we look at complexity, as I said before, we might look at, for instance, linear search over n items. I could have the best case is one step, I get lucky, I find it at the beginning. I could have the worst case, where it takes n steps. It could be in the last place in the array, or maybe it doesn't exist at all. Maybe the thing you're looking for isn't in there, and I have to look at every item before I know that it's not in there at all. The average case is saying, if I did this input or that input or that input, what would be the average of doing any one of those? Well, then it would be 1 plus n plus 2 plus n minus 1 plus 3 plus n minus 2, all the way divided by n over 2, because that's how many terms there would be like that. And if we average all those out, we get an average case of about n over 2. So that would be big O of n, best case would be big O of 1, worst case would be big O of n, and really we could change all of these to big thetas. This is big theta of 1, big theta of, whoops, that's terrible theta, big theta of n. Whoops, apparently I'm too close to the edge of the tablet there or something. It's getting really sloppy. And this one would be big theta of n. So we can look at best case, worst case, average case. One thing you have to remember when you're doing best, average, and worst case, and especially best case, you don't get to change n. You don't get to say, ooh, best case would be when n equals 1. No, we're not allowed to do that. I almost fell for that one once when I hadn't done complexity for a while. I was like, ooh, best case is when n is 1. And I went, no, can't do that. We got to leave n alone. N is some arbitrarily large number. We don't know how big n is. but I got to leave n alone, but I can rearrange the contents in here. I can change the contents around in any order I want to find the best or the worst case. Now, amortized complexity. So that's something I mentioned last time. So amortized complexity is a type of complexity analysis, and we're going to use it when the work versus time profile has spikes in it. And it's sometimes operations are expensive, but most times it's a small, I should say in here just small expense, it should say a small constant. It's usually, I'd say small expense is always true, small constant expense is usually true. So what this is we perform the analysis over of a sequence of inputs. So I say, hey, let's do it with size n, n plus 1, n plus 2, n plus 3. Let's analyze this over a sequence of operations. Average is different. Average case complexity is what if this happened or that happened. Let's get the average of each of those. Amortized analysis is what if this happened, then that happened, then the other thing happened. Let's average it over a section of those. So average is the average itself. When we say average complexity, the average case is if this or that happened. Amortized complexity is if this and that and the other thing happened all in a row. So an example here we've got of amortized analysis is, suppose, I just got round numbers here, suppose my cell phone is $100 a month for unlimited calls and text and everything else. So I pay $100 once every month, and that's the rate of work. That's the rate at which money leaves my pocket. So the money leaving my pocket rate is very spiky. Once a month, $100 leaves, and other parts of the month, nothing leaves my pocket. Now, let's say every month on average I make about 1,000 calls and texts. Well, then that means that each one has an effective cost of 10 cents. So we would say that the amortized cost per call or text is 10 cents. It's a small constant amount. So the amortized cost per text or call is 0.1, but the rate at which money leaves my pocket is very spiky. And we're going to do this again. We're going to look at this again in another lecture or two. We're going to redo this example and graph it all out with how a vector grows. And we're going to see it again. We're going to see it with how vector grows. We're going to see it with anything that uses a vector inside of them. We're going to see it with hash tables. When we do hash tables, we're going to come back to this amortized analysis. So if we said, like earlier last time, we talked about the pushing an object. So when we look at the asymptotic runtime complexity of push into a stack, if our stack really uses a vector behind the scenes, we've got this push. Sometimes it has to allocate more memory, but hopefully a lot of the time there's already room for it. Whoops, sorry. Apparently we're doing this today. Every once in a while I forget when things are in there. Okay, so I'm going to add a new slide in here. Oh, whoops, not layout. I want to say add a new slide in here, and then, okay, this is going to be, this is a pain in the butt. Okay, hold on a second. When I change this on my tablet, we might have to, okay, that looks better now. Every once in a while when you go out of the presentation mode in PowerPoint and back again, it goofs up on the slides for you, but this should be looking okay now. Okay, so what we want to look at is, let's say that my underlying vector was full. Yeah, just a second, I want to draw that just a little bit better there. Man, I just cannot draw a straight line on tablet. This plastic on glass just gets to me sometimes. Okay, let's pretend those are straight lines for our axes. And this is our size, and this is our work. Okay, so right now, we're at size n out of n. And we want to add something to the vector. So, what we have to do is we've got to make the vector bigger. So to make the vector bigger, we've got to copy what's there. So that takes n amount of work to copy the vector. Now there's a little bit of constants in there, like I had to do a new, I had to copy the elements over, and then I had to do a delete. So like the new operation is a constant, the delete operation is a constant, the point to the new block of memory is a constant, but we're not really worried about the constants, we want to worry about the n's, right? So, how much bigger did I make this new block of memory? Let's assume we double it. So now, really, I went from n out of n to n out of 2n. So now I'm at n out of 2n. And then I can finish my push back. See, I was trying to add something to it. So right now I'm at n plus 1 out of 2n. And that took, notice that little tick there, that took a constant amount of work. That took O of 1 work to finish the pushback. So I said, hey, I want to push to the stack. Behind the scenes, the stack said, hold on, I got to grow it. That took n work. Then it was able to finish the push in one more piece of work. Now the nice thing here is, though, I get to push a bunch more times before I have to grow again. So I can do a bunch more pushes. I get to complete n pushes, and once I've completed n pushes, where am I? I'm now at size. My size is now 2n out of 2n, and I'm full again. So what I want to do is I want to look at all of the work inside of this box. Inside this box, when I started out and I was at n out of n until so like basically just before I was at n out of n until just before I was at 2n out of 2n. So we want to look at the total amount of work inside that box. So the total work is equal to 2n. That's the doubling right here and all of these little ones that got added on. So the total work was 2n, but that was for a number of pushes was equal to n. Now that means the amortized cost of one push is equal to 2n divided by n is equal to 2, which is equal to big O of 1 amortized. It's big O of 1 amortized cost. So if I do a bunch of pushes, effectively each push is a constant cost. Sometimes there's a big one, then there's a lot of small ones. And if we did this again, if we made another window over here, now granted my work is all in the way of it, but what if we went from here to another one? I went from 2n out of 2n up until it was at 4n out of 4n. I could do this all over again and I'd get a constant amount. So what this is showing is if we do enough pushes in sequence, each push effectively has a constant cost. Even though some of them are bigger, some of them are smaller, amortized cost is O of 1. So behind the scenes, this is all happening automatically to the vector. Okay, so we basically, this hidden slide, we just went through all of that work by hand. Okay, so when we start looking at going from, hey, so our analysis to applying what we know about this, we do these algorithm comparisons independent of hardware, compilers, and even implementation. We want to talk about, first, we want to talk about the algorithm. What is the complexity of the algorithm before we implement it at all? And we want to be able to predict which algorithm will be faster. Now, sometimes if n is really, really small, a terrible complexity can look better. At n equals 1, 10 to the nth looks better than 20n. But at larger n, hey, that 10n is bigger. We don't care about the small n. We care about, as n gets larger beyond our control, what is our overall complexity. Now, here's the last thing we're going to do today. I want you to think about this for a minute. Let's say you go out and play some pool. And you're playing pool and you think, it seems like sometimes when you hit the cue ball and it hits another ball, it doesn't seem like that ball is moving as far as you would expect. You suspect that one of those pool balls is heavier than the others. Now, you don't have any equipment with you, but hey, if we take a pencil and we borrow a tray from our weight person, assuming that this was normal times and we were actually in a pool hall and there was someone waiting on us. So we could take that tray, we could take 2 bowls of equivalent size, and we could put, like, let's say 1 or 2 billiard balls in each side and weigh them. And we could say, hey, those 2 weigh the same as those other 2. So this is all we've got. We've got a balance beam that we made out of a pencil, a tray, and some bowls. So what I want you to think of is, how could we find the heavy ball using different complexity algorithms? How could we find it using n squared? How could we use it? How could we find it using O of n time, log of n time? Now, some of these I found it actually hard to make an n squared algorithm because I just didn't think that way. But take a minute to think about this, and we'll come back and look at the answers. Okay, so it looks like some people are getting the n squared one. What about an O of n? Okay, so I see a log of n. We got to cut them in half, and the n would be comparing one ball to all the others. Yeah. So let's run through these slides real quick. So the n, if we do an n squared algorithm for n balls, we've got to compare every ball to every other ball. Now, this seems like too much work because you'd think if one of them weighs different, we would find it before we reach n squared. The only advantage to the n squared algorithm is if we weigh all of them, maybe we'll find that, hey, I was wrong. There are 2 balls that weigh different from all the others, and the n squared would find 2 of them. But if I was right and there was only 1, we don't need n squared time. So if we just take 1 ball and compare it against the n minus 1 other ones, we get O of n time. Now, what about log time? So log time, we could split them into 2 groups. And we keep dividing them into 2 groups. It says, why is it sometimes problematical? Well, maybe there's an odd number of balls. Maybe there's 9 of them. And I've got to do something there where I've got like 4 and 4. Okay, so if there's 9, or let's say 15. There's 15 balls to begin with. I weigh 7 versus 7. If these weigh the same, the odd one out must be the one that weighs different. If these weigh different, so if this one is heavier, then I split that one into 2 groups. Oh, maybe I have to leave one out. So sometimes I have to leave one out when we don't have exactly a multiple of what I'm dividing by. Now it said come up with a log n and come up with another log n. Okay, so what's another log n? I think I saw someone say it. was 3 groups. What if we split them into 3 groups? We split 15 into 5, 5, and 5. So I've got 5 versus 5. If these weigh the same, then this group must be the odd one. Okay, what about this one? So we're almost done, I promise. We're over by a few minutes here. So is this true or false? If we've got these two approaches, log 3 or log 2, asymptotically, are they different complexity classes? And to answer this one, you actually need to go back to that table of relationships that we gave you. So remember, things that are different bases only differ by a factor of log A. 2 different logarithms of the same x. So if n doesn't change, so x here, we could replace this with n. So log base 2 of n and log base 3 of n only differ by a log of 2 or a log of 3. So these are within a constant factor of each other, and we're allowed to drop the constant. Now, last question. If we can divide it into 2, and we can divide it into 3, what if we divide it into 4 piles? Does that gain us anything? No, because I can only weigh 2 at a time. If these 2 weigh the same, I haven't learned anything about the 2 that I didn't weigh at all. So going beyond log base 3 doesn't really help here. Now, this is asymptotically. Asymptotically, they are the same. If n was large enough, I would expect log base 3 to run a little bit faster, but not a huge amount faster. Asymptotically, they're the same, but in real runtime, we'd expect the one with the smaller constant to be a little bit faster. And if n becomes large enough, that constant factor might make a noticeable difference in runtime. Okay, last question here. We're going to come back to this one next time. How could you do x to the n power, assuming integers? We don't want to bother with doubles. Obviously, we can do it with multiplications, n multiplications. What about doing it with log n multiplications? So think about that one, and we'll come back to code for this one next time.